what is in the app on I think this is the fourth or the fifth part of this kata, as we can all realize now, is that this kata is really challenging, kinda hard, and like I'm just tired. I want to finish it, you know. So let's see. Check if binary number is can be divided by 5. Is there a pattern? All right. Yeah, it's this one, look. Oh my god. Huh. Alright, yeah, so basically we get this finite state machine that we also have over here, and I think that these two are pretty much the same. So except that over here it is explicitly said that the accepting state is also start state, and we got pointer from 2 and 0 back to it, and everything else. The 4 is over here, so we can help ourselves with this one or this one now. Alright. I mean, if you just go start typing away, I mean, that would be the best. Let's see what kind of problem we get. Pattern, row, string, movement, stick it up, right. That's how it's done. Alright, so with these states, we start over here, and we can do as 0 or multiple zeros, and or, so let's make that in groups. First is 0 or multiple zeros, and then 1, 1. That's the first one, and the first one can be done also how many times? 1 or more, or multiple times. Alright, let's just write groups for each of the stages. That's for the first stage, I mean the first or 0th stage. Now if we look, if you look at the first one, then it gets complicated. It gets a little bit more complicated, because this thing branches out. So we do a YOLO. We say you can either do 1, this means we go over here and then we do Like we go over here and if you make another one, alright, let's just go group by group, you know? Let's just go group by group. 1 or 0. Both ones. And right now we are here or here. Yo, alright, this is so confusing, man. Using some methods, yo, how convert to regular expressions that accepts into minimal NFA. Thompson's algorithm. What into equivalent regular expressions? Computer science stack exchange. That sounds dope. Alright. There are several methods to do the conversion from finite automatic to regular expressions. Here I will describe the one usually taught in school, which is very visual. I believe it is the most used in practice. However, writing the algorithm is not such a good idea. State removal method. This algorithm is about handling the graph of the automation and is thus not very suitable for algorithms since it needs graph primitives such as state removal. I will describe it using higher level primitives. The key idea. The idea is to consider that regular expressions on edges and then removing intermediate states while keeping the edges labels consistent. The main pattern can be seen in the following two figures. The first has labels between P, Q, R that are regular expressions E, F, G, H, I, and we want to remove G. Alright, once removed, we compose so we say once removed we can go E, F, G, E together, preserving the edges. Okay, between P and R, but not explaining this. Alright, now you removed that. Example, using the same example as in Raphael's answer, which I guess is this one, yeah. What do? You just remove those stuff. And then to a single one. Oh my god. Algorithm. Cons. A lot of cases in this algorithm, for example, choosing which node we should remove, the number of final states at the end, and the fact that the final state can be initial too. Note that how the algorithm is written, this is a lot like the transitive closure method, only the context of the usage is different. I do not recommend implementing the algorithm, but using the method to do that by hand is a good idea, and that's what we are doing. So if we could maybe remove these two steps, that would be hell lekker. No. Alright, let's go into the sketchpad again, make a new one, and we say like we got that already. It's 0, like this is the start and the end, and we go to 1, and thing is it can like go like it's 1 and then 0, it goes back. Okay, now this is kind of grotesque. This big ass. Alright, let's just put it over here so we can switch between them quite fast. Right, it's a little bit more neatly, you know. So this is 1, and what we do is make like you can go like this with 1 and 0. Here's 1, and that's about it for 1. And there is the second one, which which is also pretty simple. It's first 0, like it's like this, you know. It's also kind of a self loop. First is also 0, then it's 1, but 0 or multiple times, then is 0. Oh man. And then it can be 0 or 1, you know. So this thing can go basically back to here. But alright, let's do it. So if this is a self loop, this is 0 and then it's 1, it goes back. Or we can also make like 2 to 1, it goes like 0, 1 star, 0 and 0. So we say 0, 1 star, 1 star, 0, 0. Or we can go way back to the accepting state with 1. Now, alright, I can write it a little bit neater, you know, so it's nice and clean, you know. Alright, I'll pause this video because I got a phone call. Pause.